Let's before we talk about the lemma, we need to define the cover time. Cover time is pretty intuitive, right? So we start with any particular node. Let's say that is V, and then we really just let the random walker visit the entire graph. We can talk about the cover time of V. It's really just that we start with the random walk, start at the position V. How long? Like of course, like in expectation, it is going to take. To cover the entire graph. Cover the entire graph means that for any state u that's in the graph in the graph, its u is visited at least once. Right. So you can sort of see that this expected time let's say this is the CV. This has to be finite. In what sense, right? So if I start with a particular node V, if I just say that I want to cover a particular node U, right? So let's pull out any edges, right? All right. So now there's actually because this is connected, right? So there's always at least one edge that's connected from U to V, right? So what's the probability that I directly travel along this edge from U to V, right? Directly travel along this purple edge, right? So this probability is not large, it's small, but it's greater than 1, greater than 0, right? So in case this event happens, right? So basically the amount of time that I'm going to spend from travel to V to U is actually going to be bounded by the length of the path, which is at most E, right? Because there's no cycle, right? So now, with non-zero probability, I'm able to travel that to U. But in case I'm being unlucky, I travel to a different place. Let's call this as U2, right? I can ask the same question, right? So I start again. I really just want to visit U. Then I can find another path. I can try again. Like there's another path connecting between U2 and U, right? So another path connecting between U2 and U. And again, with a very small but non-zero probability that I'm lucky enough to travel to use the entire path to travel to U. Which really just means that with constant amount of time, right, in expectation, I will eventually be able to hit U. And the same argument applies for every single node, right? So it's actually not difficult to show that the cover time of any CV for any V, like the cover time of V, right? Cover time of V really just means that I start the random walk starting from V, right? So this cover time in expectation is less than infinite. Then we can talk about the cover time of the graph. It's really just the worst case cover time. Right, so I start with every single node. I compute the expected cover time, and I pick up the worst case one, and that would be the cover time for the graph G. Right. So now we are going to talk about two lemmas related to the cover time. The first lemma is going to be it's really just direct application of what we talk about the commute time. The cover time G equal to VE is bounded above by 2E V minus 1. Right. How do we prove that? Like that's actually a pretty silly proof, right? So let me start with a graph, right? So this is a graph, right? So I'm not drawing the edges, right? So start with a graph, and I can always find a spanning tree. Spanning tree basically is that actually let me draw the graph out, right? So this would be my graph, right? Right. So let me just say this is graph. Spanning tree basically is that subgraph that's connected, and then that's that subgraph or the original graph that's connected, and that's also a tree, right? So this would be the purple one would be an example of the spanning tree. Right, so this would be a spanning tree, right? So A, B, C, D, E, F, G, right? So in case it's not clear, let me just use a different color, right? So this is a spanning tree over here, right? So the edges over here are not on the tree, so right, we don't care, right? So let me just redraw the spanning tree over here, right? So it's starting with A, and then it moves to B, F, and G, right? So there's 3 edges here. G has no children, F has 3 children, right? So that would be the spanning tree if I expand everything out here. This is F, C, D, E. Right. So now if I have a spanning tree, and then like starting with the spanning tree, then the next thing I'm going to get is that I actually has a way to traverse all nodes on the tree. So how do I traverse? So I can really just use the so-called standard the depth first search travel, right? So A to B, B to A, A to F, like I just traveled along this way. Right? You can sort of see that. Right. So this is really just the using the, let's call the DFS travel. Right. So in this particular example, it really becomes A to B, B to A to F, F to C, C to F, F to D, D to F, F to E, and E to F, and F to A to G, right? So this is how we travel, right? So for any tree, there's always exists this way to do the traveling. So so now what we really need to do is really just to compute the expected time to travel from A to B and B to A and so on and so forth. Really just I'm interested in travel to understand the expected time to do the entire traveling. Right? So that would be one possible way to cover all the nodes. Right? This is really just one possible way, right? So this is definitely greater than equal than the cover time. So again, like it doesn't really matter whether we travel from A or travel from anything else. It's using the same set of argument, right? So the worst case, the quantifier doesn't play too much role here, right? So we don't need to worry too much about the worst case quantifier, right? So now this is really just by the linearity. It's really just that we can compute the expected time from A to B plus expected time B to A, right? Plus and so on and so forth, right? So plus all the A down to expected time A to G, right? Expected time A to B is really just HAB, right, plus HBA, right, so on and so forth, plus HA to G, right? So now each of this is really just less than 2E, right? So less than equal to 2E, and so on and so forth, 2E, right? And how long is the entire path, right? So this is the question, right? So basically, for each term we use the same upper bound to bound that, right? So it really just reduces to question the number of terms, like what's an upper bound on the number of terms in this equality, right? So number of terms here is really just the length of the path. The length of path is really just the 2 times of the number of edges in the tree, right? So basically, if you look at this tree, right? So each edge is traversed exactly twice in order to form this kind of DFS-based traveling, depth first search-based traveling, right? So basically, this is 2 times the number of edges, right? But what would be the number of edges on the tree? The number of edges on the tree is really just the V minus 1, right? So if I have tree that has 3 nodes, then we have 2 edges. If we have a tree that has 4 nodes, 1, 2, 3, 4, 5 nodes, then we have 4 edges, right? So the number of edges is really just the number of nodes minus 1, right? This is V minus 1, this is 2 times E, and then 2 times E, right? So this is going to 4 times E and V minus 1. So the textbook gives you a tighter bound, like from 4 to 2, right? This is what the textbook gives you, right? So this is actually utilizing that if we do the pairing a little bit carefully, right? So if I look at any, like, so just now what we were doing is that so for instance, I consider this particular edge, it's traversed twice, right? So from H, E, F to C, and then again it's edge C to F, right? So for just now, what we did is that for each of the bound, we use the lemma the previous lemma, right? So the only half of the previous lemma. So what we were doing here is that we were sort of using the half of the previous lemma. Were we still able to do that, right? So I was not able to do that to find that, right? So it's actually, I switch to all the way up to, it's too much, right? So so just now we really just use the simplification of that. We say that each term is going to be less than 2e, and if we are careful, we are doing if we are pairing things up a little bit carefully, say that if you look at this edge, we're pairing up two terms, at least the edge, like edge F to C and C to F. If I pair up these two terms carefully and apply the lemma only once, then I'm able to like improve this constant from 4 to 2. But it's following the same idea, right? So I'm not going to, I think you will be able to figure that out on your own, right? So, but the whole idea is pretty straightforward, right? So the idea is that you can traverse along the spanning tree, and in order to count how much can you, how fast can you traverse along the spanning tree, you invoke the previous lemma, right? So that's lemma 7.15, and we can also have a different way to bound the cover time, right? So that's lemma 7.16, right? So the cover time g can also be expressed as g less than or equal to h n minus 1 times max uv belonging to the v, like h uv, right? So h here is the harmonic sequence, right? So the definition is right 1 over 2, 1 over 2, 1 over 3, all the way down to 1 over n minus 1. So this is the definition of a harmonic sequence, right? So now this is a second way of bounding this covering time, right? So the first way is really just saying that the covering time it's 2 times e v minus 1, right? So this is really just the that's even oblivious to the structure of the graph, right? So if you look at count the edges, count the vertices, right? So it doesn't really tell you too much about the information of the graph. Here we are sort of trying to relate the cover time with the commute time, right? So that basically says that like if I use the worst case the commute time and times something that's this whole thing is log n, then I will get the cover time, right? So the commute time and the cover time is off by a factor of log n. So so when there's a factor of log n, what can you think of, right? So this is really more or less resembles the coupon collector problem, right? So if I have n different types of coupon, right? So in order to really collect all of them, as we mentioned that like this, and we need to pay an additional factor of n, right? Here we are doing another n over here, right? So you can sort of see that this is implicitly related to the coupon collector problem, right? So and then we are going to it's indeed that there's some component of the analysis that points back to the coupon collecting problem, right? So let's try to see whether we can prove that. This is lemma 7.16. Like you can also look at the textbook, right? So let's say we have a proof, right? So let's really just for convenience, let's really just define the b as this max of u v u doesn't equal to v, like h u v, right? So this is really just I'm just drawing this this term again, like let's call the whole thing is b, right? So now here we start to want to be a bit careful, right? So what we are going to do is construct a sequence of random variable. So a sequence of random variable. All right, so this random variable is constructed on our own, and it's not related to the random walk, right? It's really just for the purpose of building the proof, we construct some artifacts, right? So let's say this random variable z1, z2, zn, right, would really just be a permutation, permutation on n, right? So a random permutation. What do I mean, right? So let's say n equal to 3. Right, then the set of all possible permutation is 3 factorials: 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Right, so there are 6 permutations, right? So I just randomly choose one, right? So in case I choose that 2, 1, 3, it's really just saying that the z1 equal to 2, z2 equal to 1, and e3 equal to 3, right? So this is how do I say that, how do we define the random permutation, right? So look at all possible permutation, randomly pick one. And then we just use z1 up to zn to denote our permutation, right? So now, after that, let's also define, right? So let also zti be the first time we visit all nodes in z1 up to zj. What does that mean? So let me just look at let me just say that let's say that I have a permutation, let's say n equal to 10, right? So just now I want to use this example, but it's too small, right? Let's say that I have a realization of the random permutation z5, e6, and all the way down to z10, right? So this is 10, this is 8, this is 2, this is 5, and this is 6, and so on and so forth. Right? So now let's give you an example of j equal to 5. J equal to 5 means z1, z2, z3, all the way down to z5, right? It's really just that I look at all these numbers. It's 5, it's 10, 8, 2, 5, 6, right? Then tj basically is the first time I visit all these nodes, all 10, 8, 2, 5, 6. This is the first time I visit all of them, right? Right. So now I want to be able to compute tj, right? So now in order to compute that, so we sort of use the same trick as we did for the coupon collector, right? So at the same time, let's also before we really proceed, let's also define another set of variables, x1, x2, all the way down to xt. This is really just denote the random walk. Right. Random walk basically says that if I start with the position u and move to the v1, v2, v3, and so on and so forth, then my x1 equal to u, x2 equal to v1, x3 equal to v2, and so on and so forth, right? So this would be the random walk sequence. Right. So now let's reapply the same trick as we did for the coupon collector problem, right? So let's define yj equal to expectation of tj minus 1, condition on if I know all z1 up to zj, and then I know x1 up to xtj minus 1. Right. What does that mean? That means that after I arrived at tj minus 1, that really means that I visited all the nodes that appeared in z1 up to zj minus 1. Then what's the amount of time, this is yj, what's the amount of time that's needed for me to visit one extra node? Zj minus 1, zj, right? So this is really just resembles in the coupon collector problem, like we collect a new coupon, right? So now the cover time. So now we can really just write down the expected cover time from u is really just that j equal to 2 to n yj plus e of t1. Right? So this is really just the telescoping. Right? So at the end, we care about Tn. Tn is really just the first time I visit all z1 up to zn, right? So, but this is the entire set, right? So Tn is what we care about, right? And in order to compute that, we just do a bit of telescoping. Tn minus 1 plus Tn minus 1 plus minus Tm minus 2 and plus and so on and so forth, right? So if I look at the gap here, this is y is it n or n minus 1, right? So this is yn, this is if I look at here, this is yn minus 1 and so on and so forth, right? So this would really just be that yn plus yn minus 1 plus so on and so forth, right? So just recall that when we define y, it comes with the expectation, right? So we don't need to write the expectation again here, right? Plus y2, right? So the first term is that we have to write this carefully, expectation of t1. Right. So now let's start with a warm-up exercise, right? So what would be the expectation of t1? So just using, so we start with the node u, right? This is the known, this is given. We start with the node u, an arbitrary node u, right? This is given. And then what we did is that we do a random permutation, z1, z2, up to zn, right? So I randomly shuffle my all node. What's the likelihood that z1 equal to u? Because everything is randomly shuffled, right? So the first point is actually a random point, right? So this is the reason that we have probability z1 equal to u is m1 over n. Right? So in case this event happens, right? So what is the expectation of t1? Right? Condition on z1 equal to u, right? So this really just recall that this is the time needed to visit u, right? So but I'm already start with the u, right? So to visit time needed to visit z1, which is u, right? So I'm already start with u, which means that I'm already start with z1, right? That really means that this is going to be 0, right? This is the first case, right? The more likely case is that the z1 is not u, right? In this case, we want to compute the expectation of t1, z1 is not u, right? It's really just that I start with I start with u, and there's another node z1. What's the expected time to travel from u to z1? It's really just the h, u, and z1, right? So, and this, as we said, is bounded by b, right? So in this case, it's actually b. So now if I compute the expectation of t1, it's really just that we can do a bit of a conditional expectation, z1 equal to u times probability of z1 equal to u, and plus expectation of t1, condition on z1 doesn't equal to u, and probability of z1 doesn't equal to u, right? So if I expand everything, it's really just that this is 0, and this is 0, and then this is 1 over n, this is 1 minus 1 over n, and then this is b, right? Bounded by b, right? So less than equal to b times 1 minus 1 over n. Right. Now, this is the first thing. Now, the second thing is that I want to compute the yj. How do I compute this one? Right. So now we want to compute the yj. What is yj, right? So it's really just time. Let's really just expand the concepts again. The time it takes to visit z1 up to zj, right? So now there are two cases, right? The case one is that let's say that at t, let's say that as tj. What's the I'm not saying the two cases first. Let me ask this question first, and then determine what are the two cases. Which node the tj visits? Right. There are two cases. The first case one is that if I look at my random walk at tj, it's really just the zj, and in the second case it is not zj, right? The second case is easier. tj is not zj. How can this happen? Right? Really, just it's really just definitional issues. But let's really just walk through how can this happen. Now let's even assume that we just now have an example. Do we have an example over here? Actually, a very it's right here. It's 10A256, right? So let's say my z1, z2, 10A256, right? So z3. Z4, Z5 is 10A256, right? So let's say my random walk really versus 10 first, versus 9, versus 8, versus 2, 5, versus 4, versus 6, versus 2, right? So let's really just look at this time step first. The T1, right? So in the first step, like I visit 10, right? In the T2, I visit 10, 9, and the T3, I visit 10, 9, 8, 10, 9, 8, right? And you sort of can verify that only up to this point, 10, 1, 2, 3, 4, 5, 6, 7, right? So up to T7, I have 10, 9, 8, 5, 4, 6, 2, right? This is actually contains everything here. If I look at T4, T6, right, it only has 10, 9, 8, 5, 4, 6. It doesn't have 2, right? When it doesn't have 2, right, so 2 is missing, right? So even in T6, it does not fully cover the set of Z1 up to Z5, right? Right. Only at when t equal to 7, it covers everything. Right. So just notice that like there are some elements that we really just accidentally covered, right? So 9 is actually not in this sixth set, and 4 is also not in this set, right? We are allowed to accidentally cover more nodes than the set we look for, but at the end we really need to cover everything because 2 were not here in the T6, right? So T6 is not really the what we want to do, right? So that really just means that my T5, it's this is t equal to 1, t equal to 2, t equal to 3, t equal to 4, and so on. So t equal to 6 and t equal to 7, right? So I don't want to confuse you, right? So my T5 is the time it takes to cover Z1 up to Z5, right? So this is going to be 7, and it takes me 7 steps, right? So in here, right? So I'm covering the second node, right? So let me just erase a little bit of things, right? So at t equal to at t equal to 7, I am visiting the second node. Whereas if I look at this, I draw this, let me just draw everything here again, 10, 8, 2, 5, 6, right? So Z1, Z2, Z4, 3, Z4, Z5, right? 10, 8, 2, 5, 6, 2, 5, 6, right? So it's t equal to 7, I'm visiting the second node. This is actually correspond to the second case where xtj doesn't equal to Z2. Z5, right? Z5 here is actually the 6th node. We can sort of see that the 6th node is actually visited early on before the second node, right? So what can we say about that, right? We can actually say that, right? So not only T5 equal to 7, we know that T4 is also equal to 7, right? Why is that, right? So if I look at T4, it's 10, 8, 2, 5, right? So this is really just the first four nodes here, right? So when T4 equal to 7, really why T4 needs to be 7? This is again that we are really missing the second node, right? So we can even say that T3 is actually equal to 7, 10, 8, 2, because the second node is not visited until the 7th step, right? Well, what does that mean, right? So we sort of let Y4 equal to the delta, the T4 equal minus T3 equal to 0, and Y5 equal to T5 minus T4 equal to 0, right? So that means that in the second case where xtj doesn't equal to zj, we do imply tj minus 1 equal to tj, right? This also implies yj is 0, right? This is the second case, yj is 0, right? In the first case, it's what that I have j node up to j nodes, right? So and at the time t, right? So let's use the red dot to draw my random walk. Xtj is actually equal to zj, right? And now we can sort of see that we can sort of like try to use the the commute time to try to figure out what is the yj. How can I do that, right? So now let me just draw everything here clean here, right? So the case 2, right? It's the tj does not visit zj, right? This implies yj equal to 0. And in the first case, tj visits zj, right? So now I'm trying to figure out what's going on from tj minus 1 to tj. So from tj minus 1, this point is that I visit the nodes z1 up to zj minus 1, right? So everything is visited once, right? And let's say that I am at a certain node here, right? This node has to belong one of them, right? tj minus 1 has to be, xtj minus 1 has to be inside one of the first j minus 1 node. Why is that? Because that, like, just imagine that if my tj minus 1 is not here, right? So let's say this is an arbitrary node that's not inside, then if I look at the tj minus 1 minus 1, right? So if I look at this step, right, I compare all the nodes that are visited up to this point and also the node that's visited and tj minus 1, right? So I'm visiting a node that's irrelevant, that's not helping me to cover more. Right? If at this stage I'm covering all the nodes here and I'm visiting an irrelevant node, that really just means that at the stage, if I look at one step ahead, this already covers all the nodes here, right? So that basically means that tj is defined in the wrong way, right? So in other words, at time tj minus 1, xtj minus 1 has to be one of them. So now I'm really just visiting from one of this node. Let's say that this is zi, I has to be less than or equal to 1, right? So I need to consider the amount of time I need to take in order to travel from zi to zj. Right? So this is actually the commute time, right? H zi zj, right? So this is actually bounded by b. Right? So in the second, so that really just means that in the first case, this happens. This yj is actually less than or equal to b. Right. So again, we sort of want to compute the y expectation of yj, right? Condition on expectation of yj. Let's not even say condition, right? So now let me really just so actually let me be a bit more careful. It's not expectation of yj, right? So let me really pull back the definition of yj, right? What's the definition of yj here, right? So all the way up here, right? So yj is a very large crap, right? So it's actually an expectation. Let me just copy and paste the whole things here and see what we can do here with this yj, right? yj equal to expectation of tj minus 1, condition on z1 up to zj, and x1 up to xtj minus 1, right? So now I sort of want to use the conditional expectation to expand this term, right? So we have the case 1 and case 2, right? Case 2 really means that my tj hits zj, and this is otherwise. Case 2 is otherwise. Case 1 is that my zj hits zj, right? So I use these two cases to split the probability, right? So this is really just expectation of tj minus tj minus 1, condition on the z1 up to zj, x1 up to xtj minus 1, and the condition on case 1, right? So let me just write this one. And the additional thing that is case 1 also happening, and probability of case 1, condition on z1 up to zj, x1 all the way down to, right? So this is really just that we need to write down the conditional probability expectation carefully when the expectation we want to compute has some conditional things going on, right? So let me just rewrite everything to make it clear, right? So this is expectation of tj, right? So I'm rewriting everything, minus tj minus 1, condition on z1 up to zj, x1 up to xtj minus 1. This is the first term, and the case 1 happens, and probability of case 1 happens, condition on everything. I copy everything here, right? z1 up to zj, and x1 up to xtj minus 1. So this is the first case, right? And I need to repeat everything, right? So it's a bit tedious, but let's really just be careful. Z1 up to Zj, x1, let me not write down everything, and the case 2, and the probability of case 2, condition on everything here, Z1 up to Zj, x1 all the way, right? So I'm just copying, right? So it's, everything are the same, right? So now what we just analyzed before is really just that in the case 2, in the otherwise case, this is the y is 0 and y is 0 and yj is 0. In the case 1, we use b to bound that, right? When we translate here, right, so this giant 1 becomes less than equal to b, and this giant 1 becomes 0, right? So at the end, we really have less than equal to b times probability of case 1, condition on z1 of zj, x1 up to xtj minus 1. So again, like, let's really just say that what is case 1? Let's really just write down the case 1's definition, right? Zj hits, right, sorry, it's the other way around. The xtj hits zj. Right. So now our observation here is that if I look at the case 1, probability of case 1, and if I imagine that if I just permute, I do a bit of a permutation here, z of pi 1, permutation is pi 1, pi 2, and pi j, right? If I do a bit of permutation here, these two probabilities are actually the same. We're talking about the same thing, right? So what does that mean, right? If just now I have the z1, z2, z3, z4, z5, right? So this is 10 what? Sorry, that I don't quite remember. 10A256, right? So just now I have 10A256, right? So if I just permute that, I construct another one, right? Z2, Z3, Z4, Z5, right? Just recall that these are constructed from a random manner, right? So if I permute that, I just randomly shuffle that as this is A5, A2, A2, 5, 6, 10, right? So if I just randomly shuffle all these points, then after this shuffling, I put that back to this conditional probability. It actually doesn't really impact my yj, right? Why is that? It's really just that because it's really just because that when the yj is really just defined as tj minus tj minus 1, right? So actually it does impact yj, but it doesn't impact tj. It's because that after I do this shuffling, right, in order to cover all the set of these 5 numbers, right, regardless how do I shuffle, I have to cover all of them, right? So it does not impact T5, right? Regardless how I do shuffle, right? But the way I do the shuffling impacts the probability of the case 1 happens, right? So just now the 6 appears at the end, right? So if we hit the 6, we are at the case 1. If we don't hit the 6, we are not in the case 1. But 6 can equally appear in one of these cases, right? So it's really just a random shuffle that doesn't really impact the t here, right? So that the textbook actually argues that this probability of case 1, condition on all these things, is actually 1 over j, right? Using the observation that the set matters, the order doesn't matter. So now, after we use this observation, right? So this really simplifies b divided by j, right? So then basically, we do have the yi less than equal to 1 over j. Right? So now, if I sum up everything, j equal to 2 to n yj plus e to the t1, then it will be less than equal to sum of j equal to 2 to n b divided by j plus 1 minus 1 over n times b, right? So if you do a little bit of the reordering of things, we get h of n minus 1 to b. Right? So the crucial argument here is really just this particular part. Right? So I'm giving one explanation. The key intuition here is that the set matters, the permutation doesn't matter, so you can fix the set first and do the permutation, right? Just rearrange the random ordering, and then we can come up with this term, right? So I guess you need to just stare at this problem and look at this for longer and try to internalize that. So in case this is not clear, I do encourage you to come to the office hour, and I will just explain again like this particular part with you, right? So this takes me a bit of time to try to really understand what's happening here, right? By now we wrap up the entire section 6, 7, and let's see whether we have time, right? So I don't think we have time today, so let's really just wrap up here, and we're going to move to the next chapter in the next section. Thank you again.